In this PowerPoint, we're going to take a look at the first part of gases. First thing we want to look at is what a gas really is. Keeping in mind that unlike a solid or a liquid, gases will expand to fill their containers as the particles move as far apart as possible. These form homogeneous mixtures. Remembering, homogeneous means that the mixture looks the same throughout. So we don't see the individual particles of a gas. It all simply looks like one solid material. They have low densities. This is typically because they have small amounts of mass but take up large volumes. They are highly compressible due to the large amounts of empty space in between the particles. And the most important thing to note is that the pressure that we see exerted by all gases stems from their collisions with each other and their container. The kinetic molecular theory of gases tells us that gas particles have an insignificant volume. Given the small size of the particles, their overall individual volumes is insignificant. Gas particles exert no forces on each other as their collisions are elastic. Gases travel in straight lines until they collide with one another or their own container. So our particles, as you can see in the image to the right, are traveling in straight lines. They do not bend or twist or turn unless they collide. All collisions between gas particles are completely elastic, meaning that no energy is lost or gained when the particles collide. They simply collide and then bounce off each other with the same amount of energy they had when they collided. There are three forms of energy that are pertinent to our gases. First is translational. This is the energy from the movement of the molecule itself. Rotational is the energy that we see from the actual rotation of the molecule. And then vibrational is the energy from the interactions of other molecules with each other. So only vibrational here involves multiple molecules. The most important thing that we can take away from this section of gases is in this blue box. The total kinetic energy, meaning all of the energy that the particles contain, is directly proportional to its Kelvin temperature. What this means is as the Kelvin temperature increases, so does the kinetic energy of the particles, and vice versa. Remembering that temperature is merely a measurement of how much heat energy a substance contains. Let's focus now on gas pressure. Pressure is defined as the amount of force per area. If collisions occur more frequently in a container, the pressure increases. If the molecules begin to move faster, the pressure also increases. A few things can increase pressure. The biggest one is the addition of gas particles. In a closed container, if I add more particles, obviously they will collide more frequently with the container, which increases pressure. Changing the volume of the container will also change the pressure. If I increase the amount of volume in the container, there's more space for the particles to move and therefore fewer collisions. Lastly, if I change the temperature, I can also change the pressure. Remembering from the slide before, if I increase the temperature, I increase the kinetic energy of the particles. This means they're moving faster, so they're colliding harder and far more frequently. Below are the common units of pressure. Most commonly, we will see the use of atmospheres represented by ATM. Sometimes you'll see measurements in kilopascals or in millimeters of mercury. Millimeters of mercury here is typically what we measure the barometric air pressure in when we're talking weather. Torr is another common unit of measurement. You see below, that's the conversion between the 4 units of measurement here for pressure. You might want to make sure you know that, though it is provided on your equation sheet. As we talked a few slides earlier, there are a few things that affect the behavior of gas. First is volume. This is defined as the space provided for a gas to move around, meaning how big is the container. Pressure, again, the force exerted on a given area. Temperature, note we are in Kelvin, meaning we add 273 to our degrees Celsius. Lastly, we will look at moles, meaning how much gas there is in a given container. Let's take a look at a few of the gas laws. The first is Boyle's law. This is an inverse relationship, which means when one goes up, the other goes down. This formula should look relatively familiar. This is identical to the dilution formula, or M1V1 equals M2V2. We've merely substituted molarity for pressure. What we're basically looking at here is the larger the container, the smaller the pressure. Charles' law, on the other hand, is a direct relationship, meaning when one increases, so does the other. You'll note here we have two fractions rather than a linear equation. Here, V1, T1 are your initial volumes and temperatures. Note in Kelvin, V2, T2 are our new temperatures, also in Kelvin. What this basically means is when we increase the temperature, we expect that the volume of the gas will increase. Thinking about this logically, we know that by increasing the temperature, we should be increasing the kinetic energy. The more energy the particles have, the more they move and the further apart they will become. The last of our individual laws here is Gay-Lussac's law. Gay-Lussac's law correlates pressure to temperature. We already said earlier that if we increase the temperature, we expect the pressure to increase, given that the particles are moving faster and therefore colliding more frequently. This is merely a mathematical correlation. They are indeed direct, so when one goes up, so does the other. Easiest way to think about this, heat them up, speed them up. The hotter they are, the faster they're moving. To make our lives a little bit easier, we have the combined gas law. We could derive this through mathematical equations, but we're not going to. What this is an equation that now relates all three of the variables in a system: pressure, volume, and temperature. Note, you can use this equation on every single problem. Whatever variable is not provided or does not change is simply ignored in the equation. For example, if my problem gives me a change in pressure and a change in volume, but says either that my temperature is constant or doesn't say anything about temperature at all, I merely ignore T1 and T2. In doing so, I'm left with Boyle's law. Here we have an example. If I have a 1.23 liter sample of gas with a pressure of 53 torr, its pressure changes to 0.75 atmospheres at a constant temperature. What is the new volume? Well, you can see the first problem here. We've got torr and we have ATM. That won't work. So the first thing I'm going to do is convert my torr to atmospheres, given that I know the conversion factor is 1 atmosphere for every 760 torr. I'm merely dividing. Then I can identify my variables. Let's call this V1. They tell me that this 53 torr, or 0.07 atmospheres, is P1 because this pressure describes that volume. The new pressure, or P2, is 0.75. We want V2. So we have Boyle's law here, and as you can see below, we plug in P1V1 equals P2V2. Multiplying these two together, we can then divide both sides by 0.75 to get our answer. So if we take a look here, this is an example problem of something you might see on an AP exam. They do like to use graphics or diagrams so they can get an understanding of your conceptual understanding outside of your straight mathematical understanding. So the gas particles in vessel 3 here, this is a multiple part problem, at 27 degrees are represented in the diagram above. The lengths of the arrows represent the speeds of the particles. Which of the following diagrams best represents the particles when vessel 3 is heated to 127? So remember, heat them up, speed them up. We are going to see a greater movement of particles within our system. We can immediately rule out C and D. One, we didn't do any chemical reaction, so there's no reason for all of these new single atom elements floating around. We also didn't add any gas, so there's no reason that we have now more of these molecules than we did before. We expect that overall the gas particles should begin to move faster. Therefore, A would be the correct answer, as it shows the arrows getting longer, whereas in B, our arrows are getting shorter, indicating that they are slowing down.